for. So I think we're still talking about doing something on Astronomy Day, but if anybody is really in a big hurry, maybe you can contact me to see it. But yeah, I think the book is printed in the States. A lot of these books tend to be printed in Hong Kong and places like that. But I think this one, it's done in the USA, and I'm the Canadian content.
Maybe for Deborah's benefit, do you have a copy there, Chris?
Oh yeah, just right here.
I don't know if you know what we're talking about, just in case.
This is I'm a historian, and I was hired by NASA to write this book about Hubble operations.
Oh wow, that's so
And
cool.
I think there should be a few copies kicking around HIA by now, because there was a few of those folks helped me out.
Nice.
And so they got some from my first shipment. So anyway, yeah, there's a book written a number of years ago about how Hubble was built, and I wrote something about it, 30 years of operations. So
And still going.
it's still going. That's right. Yes.
Yeah, it's really cool.
Yeah, I think the idea is to get a couple of years of joint operations with JWST, and then I'm actually working on something else right now, which I hope is going to be in the Journal of the RASC in a few months or a year or so, depending on how long it takes. But the Canadian Astronomy Data Center, I mentioned it in the book, but I wasn't really able to do much work about its history, and I'm kind of working on that right now.
So Chris, are you going to queue up? Are you going to queue up to do JWST?
Yes.
Oh, you are. Oh, okay.
Or sorry.
Do the history of it.
No.
In 30 years.
No. In 30 years, I'm going to be in pretty rough shape. But the guy who wrote the first book on Hubble, a guy named Robert Smith, who is actually my PhD. What do you call it? Anyway, he was my PhD advisor. He wrote the book on how Hubble was built, and then in recent years, he's been working on how JWST was built. So I think he's now that I think he's waiting for for June, and then he's going to send his book off to be published. So he might have done this book that I did if he wasn't so busy with JWST, but he's going to do the book, and he has been working on it for a long, long time, and it's going to be fascinating, I think. I helped him out a little bit on it when I was a grad student, and that's getting to be a few years ago now. So he's been working on it for a long time.
Chris, will it be published the same way, just like your book was?
No, I imagine it will be published. I'm not sure who's going to publish it, but it will probably be like a university press or something like that. This one was published by NASA, and it was funded by NASA.
And Deborah, just to let you know too, they're giving them away. So we've just been emailing them and asking them for a copy, and some of us have already received them in the mail.
Oh wow!
And it's a beautiful book.
Yeah.
They went all out on it. I mean, it is spectacular.
Yeah.
They figure the taxpayer pays for NASA, so they can't really charge for anything.
Yeah, fully illustrated,
Yeah. And it's a hard cover. I thought it was a soft cover when you first put it up, but it's
Chris,
a gorgeous book.
Chris, are you happy with the print quality?
Yes, I'm very happy. you know, it was when I first saw the layout for it, it was kind of an emotional moment, you know, because I've done books before, but none really as nice as this one, at least in the production quality.
Yeah, it's often a rare thing these days to have a really nicely printed book.
Yeah.
It's beautiful. Mhm.
So yeah, I mean, I had some idea because I picked out a lot of the pictures, but then they did things like for chapter headings, they would take little bits from Hubble images and stuff like that, and they just went to town on those. So let's see. Yes,
And Joe has posted a reminder of where to find the information. Yes.
that's right. Or you can
Or see Chris.
or see me. Yeah.
Chris G.
Till I run out.
Chris, I ordered it through Amazon and got it almost immediately. Well, I mean,
The hard
Amazon
copy?
is genius anyway. Yeah, well, it was an e-copy,
Yes.
so
Well-
that means it's available there too.
Yes.
Amazon, this is kind of a weird thing. Amazon has e-copies, although you can get e-copies for free from the NASA website. I think you probably had to pay $2 or something like that.
It was something like that. Yeah.
And you can get them for free on the NASA website if you just like, but the hard copies are not being made directly available to Amazon. So like some will show up on Amazon, you know, like when the used copies
Yeah.
show up
Okay.
through their
Resale.
resellers. But
Yeah.
you can't go onto Amazon right now and get the hard copy. You have to you can, like I said, either see me or there's an email address at NASA. So
Anyways, yeah, well, thank you. And thank you for joining us this evening. I see we've got 33 people here so far, so I think we'll get organized to start. We have a guest speaker tonight, so I'd like to welcome Deborah Lokhost, who's going to speak to us tonight shortly. We also have three Edmonton photos. I don't know if Jim Hesser, if you want to say a bit about there's a link to Galaxy site about some galaxy atmospheres, I guess. I need to read it again. I could show that if you would like. David Lee, sorry, yeah, go ahead.
Why don't you deal with it, Chris?
Sure.
That'd be fine.
Okay, I will put that up right after Edmonton. And then David Lee asked to say a few words. I guess Chris Gainor will have an update on where we are now with James Webb. And then Jeff wanted to give a preview of, because we have another speaker next week too. Does anybody else have anything they wanted to say tonight?
Only if there's time.
Okay, so I'll make a note, Dave, that you are maybe. Great, thank you very much. Okay, so I'll turn over to Margie now, if you're ready, and we can have our guest speaker.
Okay. Deborah Lokhost is an Instrument Science Research Associate at the NRC Hertzberg Astronomy and Astrophysics Research Center in Victoria, BC. During her PhD in the Department of Astronomy and Astrophysics at U of T, she worked with the Dragonfly telephoto array to observe and study galaxies. She designed an upgrade to Dragonfly and built a Pathfinder telescope based on this design, which she then used to study gas in the surroundings of galaxies. She is currently leading the construction of a full-scale upgrade to the telescope, which has the ultimate goal of imaging gas in the cosmic web of dark matter. Deborah Lokhost, welcome.
Thank you. I'll start sharing my screen again. Great. Can you see my screen?
We can.
Perfect. Okay, yeah, thanks for inviting me to talk today. It was a great surprise to get your email, and I'm really glad that you reached out. As Margie mentioned, I'll be talking about the Dragonfly telephoto array, which I've been working on for the past few years now. And there's a glimpse of it here in this frame. But before I talk about it specifically, I was going to introduce the concept of the telescope because it is a bit of a funny looking, unique design. And then I'll talk about its discoveries and then finish up with my work on the telescope specifically. So feel free to ask questions anytime through the presentation. I know there's a mix of beginners to pro amateur astronomers, and pro astronomers. So yeah, feel free to give me any questions throughout the talk, and I'll try to tune it so it's applicable for everybody. Okay, so on topic with what we were just talking about, this is a zoom in onto the Hubble deep field, ultra deep field. So as many of you are probably aware, Hubble, one of the first things Hubble did was pick a blank spot in the sky where they couldn't see any stars or galaxies, and then they just stared at it for, I think, 11 days. And this is the image that the Hubble Space Telescope collected. So there's thousands, I think tens of 10,000 about galaxies in this image. And the Hubble Space Telescope really represents the peak of astronomical telescopes. I mean, JWST is coming, so Webb, once it's actually observing. And what I wanted to talk about is how did we get here to this telescope in particular, and how did we design telescopes as they are today, as they exist today. So the way we did it was we built larger and larger telescopes. For example, this is a image of the Yerkes 40-inch refractor telescope, which I think this image was taken in 1897, and it was the biggest telescope of its time. It's about 1 meter diameter, fully refracting telescope. And this is the 100-inch Hooker telescope, which was the next really state-of-the-art telescope. And then I think I'd say almost what people consider the best ground-based telescope today is the Keck telescope, which has a 10-meter diameter entrance aperture. And the reason that astronomers or scientists, engineers are making bigger and bigger telescope is probably obvious to many of you, but I'll go over it, is for one, the bigger you make your telescope, the bigger light gathering bucket you have. So the more photons you can collect, so the deeper image you can take. And the other reason is that the bigger you make your telescope, the higher angular resolution you have in your image. So you can image tinier and tinier things in the sky, so things that are farther and farther away. So I just included one equation because this is the basic equation that astronomers use, which is that your angular resolution goes down so you can resolve more things as your diameter of your telescope gets bigger. So that's the goal. And this increase in telescope size can be demonstrated by the number of galaxies astronomers have discovered over time. So this plot that I'm showing here is a plot of galaxies discovered by 1988. And what the axes are is the size of the galaxies versus their brightness. And immediately what you can see from this plot is that the galaxies at that time fell along this line where as they got brighter, as they got bigger, they got fainter, which doesn't actually make any physical sense because galaxies should be able to be any size and any luminosity. But the reason that this happens, that this relationship was happening, is due to biases in how we observe galaxies and how we built our telescopes. So as we built bigger and bigger telescopes, we're able to push up into this regime where we image fainter and smaller objects. And so we've managed to fill out that area a lot since this plot came out in the 80s. But this ends up leaving behind a whole vast space of objects that are very big and very faint. So they have very low surface brightness. And just to illustrate, these kinds of objects, while they have the same brightness as this kind of galaxy that was detected, instead of being concentrated over the same area, if you spread that same brightness object out over larger and larger areas, it gets very faint, very low surface brightness. And so if you're trying to image it against a noisy background, you can no longer see it. So 30 years later, astronomers were no closer to filling in this gap in phase space, this missing phase space of where galaxies should be. And the culprit that was causing astronomers not to detect these kinds of objects was light scattering in telescopes. So you can't solve this problem by building bigger telescopes, clearly, or by exposing your telescope for longer. What we need to do is to eliminate systematics. The effect of this light scattering can be illustrated in these plots where the plots have reversed brightness. So black is bright and white is dim. And as you can see, this is kind of a typical image of what you would see when you're looking at a bright star with the current modern day telescopes. And this is actually taken by a telescope that is optimized for low surface brightness imaging. And what you can see is you have these large halos around the stars, you have diffraction spikes and other sources of scattering and ghosting in your optics. And if you're trying to detect something that's very large, but also very faint, it's going to be very difficult because it's very hard to determine whether it's actually real against all this light scattering background. So there's two main problems that cause light scattering in the current conventional way to build telescopes. And the first is that they use mirrors. And the reason they use mirrors is because you can't technologically make a lens that's bigger than about a meter in diameter. Around that point, the lens itself just becomes flawed and you can no longer make anything bigger. So people, of course, turn to mirrors to start building bigger and bigger telescopes. Well, mirrors have these micro roughnesses on them, and so they cause more light scattering than you do with lenses. The other culprit is obstructions. So with your typical telescope design, as you're probably familiar with, you have the light coming in, it hits your primary mirror, gets reflected up to your secondary mirror, and then sent down into your instrument or into your eyepiece. And the way you hold that secondary mirror in place is by putting support struts up for it because it can't just float in the air. And these cause a lot of light scattering themselves. So you get these diffraction spikes. So as I alluded to earlier, you might say, let's just go back to refractors, but of course there's a limit to how big you can make these telescopes. You can't just make bigger and bigger lenses. So what's the solution? Except for a solar telescope, refractors have been dead in astronomy for over a century, but they are alive and well in the real world. And that specifically is in the field of high performance photography and imaging, such as this lens shown on the left. So companies such as Canon are continuously upgrading their telephoto lenses for professional photography in order to prevent scattering, such as you'd see in this top image. And the way that Canon recently started doing this was they're now using these nano-fabricated coatings, and they put these on their lenses and they reduce the light scattering. So you don't get any of these lens flares or scattering in your optics. So what if we could use these telephoto lenses to create an astronomical telescope? So this is the question that Bob Abraham at the University of Toronto and Peter Van Dockum at Yale asked themselves back in 2014. And that's what led to the Dragonfly telephoto array. So this is the Dragonfly telephoto array as it exists today, but it did build up over time. So they started with just one lens, and then 3, and then 8, and then made a big jump to the 48 lenses that you can see in these pictures. So we have 24 lenses per mount, and they're all Canon telephoto lenses, basically the biggest telephoto lens you can get from Canon. And they're located in New Mexico Skies Observatories, which is actually an amateur observatory in New Mexico. And the staff there help us out with our observations. So in addition to being made out of lenses and in New Mexico, it's also fully automated and robotically controlled. So we can do all the observing remotely. So the staff at New Mexico Skies, while they do help us out a lot, we mainly just loop them in when something's not working. So like if there's a connection between a camera and the computer, so that it's not taking images, that kind of thing, we can get them in to help us debug what's going on. Right now, these are where our 2 mounts are, and the rest of these domes here are actually mostly have private telescopes in them. Do you want to go ahead and ask your question?
I was just wondering why they decided to stop at 24 and go to 248s. Is it the room that they have in that dome, or is there some sort of physical reason they wanted to split it into 2 separate arrays?
So the reason it's split, and not just 48 together, is the weight restriction. So the mounts that hold the telephoto lenses together have a weight restriction of about 600 pounds, and so they had to be split between two mounts. And the reason they picked 48, that number, is that 48 because all 48 lenses are pointed at the same spot in the sky. They all take their own image, but then we almost immediately, after doing like the flat field and dark subtraction, we stack them together. So we basically just add everything together. So all 48 lenses are equivalent to about a 1 meter diameter telescope, fully refracting. So that was, I think, the goalpost for the 48.
Thank you.
So Deborah, what's the actual weight payload on the mount? How heavy is that array?
I think so. This one is probably about 500 pounds.
Wow.
I think each one. Yeah, the reason on our next one, so we're actually doing an upgrade, and that will have 30 lenses per mount, which is pushing it a bit. And that one is about 700 pounds. So this one's a bit less. We're really pushing the mounts to their limit with these.
And what mount are you using for these?
They're from Software Bisque, and they're they're Paramount mount. I forget the exact name, but I can look it up if you want after.
That's great. Thank you.
No problem. Yeah, the other thing I want to mention is we currently use a software called Astro Planner. I don't know if any of you guys have heard of it or familiar with it, and it works really well for us. And we are able, it's basically a software we can input all your targets for as long as you want, and you can give all the targets different weightings, and you can code up the weightings so they're calculated every single night based on what targets are up in the sky. And the telescope is pretty much fully automated now. Like, we just start one script and the telescope itself decides when it should take flats, what target it should observe, how long it should observe it. It figures out how good the images were, and then if it needs to re-observe. So it's very, very streamlined now, which is really nice, because it was very hard, very buggy for the first couple of years. So this is a huge improvement. And I just want to show quickly the team. So this is Bob and Peter on the left, and then a whole bunch of team members. So this team's kind of, these pictures are pretty old now, because we haven't been down there for a couple of years because of COVID. But we try to go down every year to have a team meeting down there. And we used to debug the telescope at the same time. And actually, we're going to New Mexico tomorrow. I'm flying there tomorrow for the first time in 3 years. And we're going to be setting up the next iteration of Dragonfly, which I'll talk about in a little bit. Okay, So Dragonfly has been on the sky for about 6 years now. And I just want to show an example of the difference in imaging that you get with one of the conventional telescopes. So this is the Sloan Digital Sky Survey image of just a field of the sky, and versus the Dragonfly image. So for comparison, the Sloan Digital Sky Survey is a 2.5 meter telescope just down the road from the New Mexico Skies Observatory, actually. It's at Apache Point. And the same field image with Dragonfly looks like this. So what Dragonfly's real forte is this low surface brightness structure everywhere. So here's just a side by side. And it really picks out, reduces this whole scattering issues in the frame. It also has a very wide field of view, 2 degrees by 3 degrees. So it can, you basically don't have to worry about like stacking images together. You don't have to worry about these lines caused by differences in the sky subtraction between your data. And they just get
So
stacked together.
Deborah, as a fair comparison, are these both calibrated images?
Yes, yes, they
Oh,
are.
wow, that's impressive.
Yeah. I mean, Sloan for sure has its strengths over Dragonfly, which is in the point sources. So Dragonfly does not have as high a detection sensitivity to point sources. I think Sloan does. It's just got a higher resolution and it's a bigger telescope. So it's really optimized for that over Dragonfly, which is optimized for these wide field things.
So are you just trading off, it's Dave here, you're just trading off integration time, or is it doing more than that?
So it's one big thing is the light scattering. So just these, if you look in the background here in Sloan, it's just super noisy compared to Dragonfly. But they have a higher resolution, so they can pick out these little stars and have like quite high detection to them. So it's kind of a fair comparison because they're similar in size. Not exactly, like Sloan is bigger, but and they're in the same spot, so they've got like the same seeing conditions. But yeah, they're just very different telescopes.
So Deborah, you attribute that to the special coatings on the lenses?
Yes, yeah,
Oh,
for
okay.
sure. The ones, I mean, like we haven't tried it with telephoto lenses without the special coatings, which would be interesting to test. But I think that's definitely like that reduces the reflections significantly. So I think that is a big part of this, and the fact that it's fully refracting, so you don't get any diffraction issues, which you see in here as well a little bit. Yeah. Okay. If does anyone else have questions about the technical side of Dragonfly? And I'll address those if you'd like. And before I move on to science, which is the next thing I was going to talk about.
Deborah, I'm curious why you went with kind of off the shelf commercial optics as opposed to having them developed.
Yeah, well, it's actually quite like compared to your typical professional telescope, it's very, I don't want to say cheap, but it is a lot cheaper than building like a fully refracting custom built telescope, that's for sure. And because of these custom coatings, like we'd have to spend a lot of time doing our own R&D to create these nanofabricating coatings because they're proprietary. So it just ended up being like a cost benefit analysis. It was just better to use these off the shelf components because they were so useful. And the other thing was that the plan was to disassemble Dragonfly, to actually put it on sky. It would observe for a couple of years. It would see some stuff, it'd be cool, and then it'd be done. And you'd take it apart and you'd sell the components and it'd be a complete circle. Of course, that didn't happen because we're still seeing cool stuff with Dragonfly, but maybe down the road it will still.
I wonder if budgets are going to drive people to use more commodity type components now.
Yeah, I'd be interested. It's hard to do with a big telescopes, because you just have to make, honest, it just seems for these big telescopes, you have to make such large components. They just don't make them commercially. But I think the Dragonfly idea is taking off for sure. Like there's a lot of similar design telescopes that are taking the idea and running with it. So I think it's gonna happen.
Yeah, I think with technology, quantity rules, which is why a lot of our sensor technology is driven by other industries, right?
Yeah.
So
Totally. Actually, so we've just bought a whole bunch of CCD cameras for our upgrade, and they're like the last ones almost, because technology is moving over to CMOS. So if you want these CCDs, we had to actually lock the sensors in a couple years ago in order so that we'd be able to have all the cameras we wanted. But yeah, for sure, everything is driven by industry. I think.
So, am I on?
Yeah.
Am I on? Oh, I was going to ask actually, what is on the back end of those lenses?
We have a small focuser, which is a tube, and those are from a company called Burger Engineering, and we just kind of buy them and use them straight up. And then we have the cameras on the other side, and those are cameras from Diffraction Limited, or SIG used to be, and they're just honestly, I know what their new ones are, but I forgot what the old ones are called. But they're like a
it's their new
2K
generation
by
one.
2K.
Yeah, it's their new generation ones. Yeah.
Our new generation ones that we're just buying are Illuma 694s.
That's the name. Yeah.
Diffraction Limited. Yeah. I forget what the old ones are called. They're like STS.
Yeah.
Numbers.
There was a whole family of them actually.
Right. So there's probably not very specific of me. Yeah. And then each lens has its own computer as well. And that we just have Intel sticks on this original version, and that one collects the images. And then we have one computer that uses an Internet of Things framework to talk to all of these sticks. So all the 48.
That's outrageous. You're using little Intel sticks for each camera.
And actually, we're going to Raspberry Pis now.
Oh, that's great.
So I'll let you know how it goes. Just check in with me in like a month.
I will.
Just to finish off the whole what's on the back. Are each one of those filtered as well? They have filter wheels on each one?
They just have one filter insert. So the telescopic, there's no filter wheel. In the lens itself, we just put a filter in the back. There's an insert in the telephoto lens.
Yeah, little drop in. And you just put a. Yeah. So what filter are you using?
These ones for this Dragonfly, the 48, we use Sloan Digital Sky Survey copycat filters, G and R. So we just split half and half G and half R.
Okay. So you're kind of making a sort of almost a bare array out of different cameras rather than the sensors.
Yeah. So you're using photometrics then, really, yes. Right, Deborah? Yeah.
Yes. Actually, I think you can see there. Yeah. You can see the reflection from the different. No, pause. No, sorry. Well, you can see it for a second there. Your reflection from the two different filters.
Thank you.
Okay. Was there another question, or should I move on?
It was for me. Maybe I missed it in Marjorie's introduction, but Dragonfly, because the array looks like the eyes of a dragonfly.
Yes, that's right. And also Peter from Yale, he's a amateur photographer, and he likes to photograph dragonflies. And he actually has a book filled with photos of dragonflies that you can buy on Amazon. So that was the other reason. Yeah. All right, I'll move on to science. So before I talk about my own research and my own work with Dragonfly, I want to highlight some of the really cool work and discoveries that have been carried out with Dragonfly so far by my colleagues and me peripherally. And of course, the main target for Dragonfly is galaxies. If you remember that plot I showed earlier, one of the real drivers behind creating the Dragonfly telephoto array was to try to fill out the space where we were missing detections of galaxies. So this is you guys are all familiar with galaxies, I'm sure. These are all galaxies, lots of galaxies. And the definition of a galaxy broadly is that it's a collection of gas, dust, stars, and dark matter bound by gravity. And one of the big questions in astronomy that still exists is, what is dark matter? And I just wanted to introduce it quickly because I'll be addressing it in a little bit, talking about these discoveries. So the idea is that if you measure the velocity of stars inside a galaxy, and you do that as a function of how far they are from the center of galaxies, you can just use the laws of gravity to figure out how fast those stars should be going based on how much mass is inside that galaxy. So you just count up all the stars, figure out how much mass there is, and then this curve of velocity is what you get. So the velocity of the star should increase until you've reached about the edge of where most of the mass of the stars is, and then it should drop. But what people actually observed was that the measured speed of these stars just kept going up. So it didn't do this drop like they expected it to, based on the stars and the gas and everything you could see inside the galaxy. So the stars have these much higher speeds than they're supposed to. And the reason, and basically the only possible solution to this is that there's some kind of mass, some kind of matter inside these galaxies that we can't see. And there's a lot of it, because this is a very large difference between the velocities that we measured and that there should theoretically be from just the stars. And that matter, because we couldn't see it, we didn't know what it was, astronomers called it dark matter. So that's the basic beginnings of dark matter. And I just wanted to pop up this plot, which is basically the same, but this is the actual first detection of dark matter indirectly by Vera Rubin. And as you can see, it's basically exactly what I told you. The velocity should follow this curve, but actually they just keep rising and then flatten off. So there must be this huge contribution from the halo of the galaxy. So to give you a kind of a reference point, in the Milky Way, there's 50 billion times the mass of the sun in stars. But if you measure the velocities and you add up all the matter that's actually there, there's 700 billion times the mass of the sun in dark matter. So about 90% of our galaxy is dark matter, this matter that we can't see and we don't know what it is. And this is about a typical proportion of stars to dark matter in galaxies. So this is just kind of a reference. So one thing we also wanted to do with Dragonfly was to investigate dark matter. So just keep this in the back of your mind and we'll come back to it later. So back to Dragonfly, what we first did, this is right when I was starting with Dragonfly, was he stared at a cluster of galaxies. So this is the Coma cluster of galaxies. And most of all these bright things are galaxies, and a lot of the other point sources are galaxies in this image. And the Dragonfly just stared at that Coma galaxy to try to see what they would see and whether they would find anything other than the galaxies that had already been seen inside that cluster. And they did. So all these red squares are these new things, blobs, that Dragonfly discovered. So if we zoom in on a few of them, this is what they look like in the Dragonfly data. They're definitely something there, but they just look like blobs, but they are real for sure. And what you can also do is look at these same spots with another telescope, and this kind of also gives you an illustration, like with the Sloan, like I did with the Sloan Sky Survey earlier. And as you can see with the Canada, France, Hawaii telescope, you do see something there, especially for the brighter ones, but it's basically so faint that you don't know if it's real or not if you just look at these data. So these blobs, the Dragonfly team dubbed them ultra diffuse galaxies. ultra diffuse galaxies. So yeah, then if you take all these galaxies and you plot them on the same plot as we did before, so I'll just whip that around and mirror it so it's the same orientation. You can see all the new galaxies, all these ultra diffuse galaxies that Dragonfly discovered fit right inside this section that no galaxies had been discovered before. So Dragonfly ended up being good at what it was designed to do, what it thought would be designed to do, which is to discover these really faint, blobby, large features. So as an example of what these look like compared to other galaxies, so most of these M33, M31, M104, M82, you've probably seen these before. These are your typical galaxies. And on the same scale, this is what an ultra diffuse galaxy would look like. So super faint, almost not there. And yeah, so these had been seen before a couple times, but this was the first time that they'd been discovered in like the tens or the hundreds. And so the next thing that the team did, that we did, was we wanted to do a few case studies, because the other question is, are these just scaled down versions of regular galaxies, or is there something different going on? Like, what about their dark matter content? Is it also strange? So we wanted to look into that a bit more. So the first single ultra diffuse galaxy that that the team followed up with, we called Dragonfly 44. And it was an ultra diffuse galaxy from that Coma cluster. And here, oh, you can see Coma cluster. I'm going to zoom in onto it. So this is the picture of Dragonfly 44 taken with Hubble, actually. And what we found with the Hubble Space Telescope was it had a bunch of bright blobs inside of it. And these were globular clusters, so clusters of stars, which is also pretty unusual to see inside a galaxy of this morphology. But I can come back to that later if there's questions. But the idea was you could take these globular clusters and measure their velocity to then do a calculation of how much mass is inside of this galaxy. And what we found was that this Dragonfly 44 contains the same amount of dark matter as the Milky Way galaxy, but 100 times less stars. So it's some kind of failed Milky Way, was how it was kind of pitched as. And so this is a interesting result, but we wanted to know if this is kind of standard, like are all ultra diffuse galaxies like that? So we went and looked at another ultra diffuse galaxy as a case study. So this time we went to the NGC 1052 group of galaxies and picked out this one ultra diffuse galaxy to study. And it also has a bunch of globular clusters that we could use to measure the velocity. And what we found was very surprising, which is that this one, in fact, had very little dark matter. It has such little dark matter that it's consistent with not having any dark matter at all. So like 400 times less than we would expect for a galaxy this size. So it's very different. So comparing the two, one of these ultra diffuse galaxies has 400 times too little dark matter, and the other one has 100 times too much for the number of stars inside of it. So it's basically just kind of starting to unveil what's going on inside these ultra diffuse galaxies, because clearly something different has been happening in both these cases, and there must be different mechanisms to create these kinds of ultra diffuse galaxies. And one interesting note I want to point out is that there are alternative theories to dark matter, such as modified Newtonian gravity, or MOND, which is basically just saying that the laws of physics change on large scales. So you have to add in other terms. And this result, where you have one galaxy with too little dark matter and one with too much, is actually an argument for dark matter, because you can't just turn the laws of physics on and off, but you can remove dark matter from something and put it in another thing. So it's much more flexible than MOND. So that's kind of all the discoveries that I want to talk about. So I can take a question if you want to go ahead there.
I had a question, Deborah, related to your discussion of the two types of clusters here with little dark matter and lots of dark matter. What have you observed, or have you been able to measure the relative gravitational forces associated with dark matter? And does that give, if you have, does that give any insight into why there might be a difference in diffusion and density?
Yeah, so if we can, basically this measurement was saying that we have less dark matter in one and more dark matter in another. And the whole, what we're using to make these kinds of statements is the idea, the theory that dark matter is made up of particles. So dark matter, the theory, the current, I think, most supported theory of dark matter is that it's made up of mostly made up of these things called WIMPs, weakly interacting massive particles. And these are just kind of your normal particle, except it doesn't interact through the strong force or the weak force or the electromagnetic force. It only interacts through gravity. And so if you take that idea, you can just kind of remove it from, you just take these standard particles, but you can put in as many as you want and make the gravitational field very high, or you can take them all out and have no gravitational field from these dark matter particles.
So
in terms
one
of
on the left, that's 400 times too little dark matter compared to the one on the right that's 100 times too much. Would the impact be that globule as an entity of itself would have less gravitational impact on the surrounding environment than the one on the right hand side? Is that the theory?
Yes.
Okay.
Yeah, that's right. So if you then think about how it would interact with other galaxies, yeah, it would have a stronger gravitational force. So it'd be able to.
And one more question, Deborah, does that lead to any kind of indication then as to why there's diffusion happening? Like are they robbing matter from each other? Is that why they're not forming like normal galaxies?
Yeah, that's a great question. And I think that is definitely an explanation for some of these, and maybe more of them. So for sure, for the one with 100 times too much dark matter, I think it's more straightforward. It's also in a very large cluster. So you've got a lot of other galaxies around that could, you've got a lot of other galaxies around that could have done flybys and stripped gas from DF44. You also have the hot intercluster medium, so this hot gas that fills clusters. And as soon as the galaxy enters into the cluster, it hits this like wall of gas. So you get this RAM pressure stripping of the galaxy itself. So this could have also been something that happened to this galaxy. It's a little harder to steal away dark matter from a galaxy, but there is an interesting theory for DF2, which is that it's basically flying by two big galaxies, and then its dark matter and its gas got separated. So there should be like a clump of dark matter somewhere nearby that we can't see, and then what we do see is just the stars formed from that gas. Yeah. So we're still trying to figure it out. But
So it's almost like the
definitely,
diffusion is more diffuse between the elements, whereas the one that has too much, it's more integrated.
yeah.
Okay.
Yeah.
Just so from your curve, you should be able to calculate the distribution of the dark matter.
Yes.
Right?
Yes.
So is it all located in the middle, or is it according to the regular mass, or is it larger?
That's a great question. So I'm not actually sure we have enough detection statistics to determine that, unfortunately. And I think, let me see if I can remember. I think for DF2, for example, we only had we only had 9 globular clusters, these 9 pointings you can see here. So there wasn't really a way to get a profile. It's easier in disks because the stars are all rotating together in a plane. So you can more clearly measure their difference in velocity and you can make a nice curve.
Yeah.
But in these fuzzy galaxies, the globular clusters are not going in a disk. They're just kind of rotating all over the place. So it's much harder to figure out what the actual velocity curve is because you have some of these globular clusters are going to be coming towards us, and them are going to be going away. Some of them are going to be going around. So instead of making a direct velocity detection, what we do is we take the velocity distribution and then we get the mass from that. So it's not as clear.
But you're probably assuming it's all in the middle somewhere at the center of the rotation.
We don't. I think we basically assume there are these huge halos in general.
Okay.
Even in here, though that's a great question because I don't quite remember. What we did do with DF44 was after we got the globular cluster velocity distribution, we measured the stars. So like we took patches of the whole galaxy and then measured the velocity from that. And we might have got a curve, but I can't remember now. That's a really good question. I can look it up and tell you later.
Just the related question is, why isn't there any of this in my backyard?
Any galaxy, any dark matter? Because it doesn't interact with us. It doesn't touch us.
It has to in a gravitational way, doesn't it?
Yeah. Yes. Yes. Yeah, actually, so it's hard to detect. So there are other experiments. So of course I'm mainly focused on these kind of indirect measurements, but it's just really hard to detect because it's so diffuse. Like if you think about these stars being diffuse, the dark matter itself is even more diffuse. So how do you measure something gravitationally affecting you when it's all around you? It's not pulling you in one direction, it's pulling you in all directions. But there are dark matter experiments, some really cool ones coming that are already online. These xenon detectors really fill I don't know the details, but they fill a vat or a lake or whatever with xenon, and then these particles should theoretically interact eventually and produce neutrinos. So then you can directly measure it, but we haven't been able to do that yet.
Yeah, it's just interesting why neutrinos aren't affecting the gravitational constant that I can calculate in my backyard.
Yeah, it's just too faint, I think.
Thanks.
Yeah, no problem.
And Lori has a question.
Oh, I think you're
yes.
muted.
Yes. So, Deborah, thank you. There was one of your slides, and I think it was actually the one that was just before this one. Do you think that you could just go
this one
back? Dear. Okay. No. Okay. No.
That one.
Oh dear. Okay. Maybe not. Oh, okay. There was a slide in which there was definitely like a diffuse, you were doing the diffuse galaxies, but there seemed to be kind of more diffuse or a little bit thicker, but still diffuse spots kind of in front of the galaxy. And I was wondering, I can't really see this right now. Maybe I don't think it was this one. Anyway, what I wanted to know was, can we sometimes see okay, so the one that ultra diffuse, the one that's right smack dab in the middle, is there seems to be some things kind of, is it in front of that diffuse gallery? Like there seem to be some kind of nice good blobs in front there. Are those other galaxies that are in front of that diffuse galaxy, or are they something else completely?
That's a great question. They're probably, most of them are galaxies behind that galaxy.
I mean, true.
And it's very hard to figure that out. And I want to bring up this one again, because as you can see, the numbers aren't like 1, 2, 3, 4, 5, 6, 7, 8, 9. They're like 73, 101. It's because we went and looked at all of these little point sources to try and find if there were any of them were globular clusters associated with this ultra diffuse galaxy. And most of them were not. Most of them were background galaxies. So you could tell by their own velocities that they were way out there and not related to this galaxy at all. So of all those that we found, which was more than 100, we only found 9 globular clusters.
And so those would be behind what we're actually looking at.
Yes. Yeah.
Okay, that's bizarre. All right. Thank you.
They're just bright. Yeah, no problem.
Deborah, could you go to your last slide again? I just had one thought I wanted to ask.
Yes. This one?
Yeah. So, you know, when you were describing this, you're talking about the gravitational variances and differences, and Dave was talking about, you know, the ability to eventually see if there's neutrino impact. It reminded me of the lecture I saw about the concept of quantum gravity and black holes, and the perspective that there might actually be white holes, so looking at space and time. And I'm wondering if you guys have questioned or asked, is the variance here in this diffusion relationship between the formation of dark matter into a compact versus maybe the expansion or birth of a dark matter that's much older perhaps in time, or reverse?
Yeah, that's very much a little bit more theoretical than we usually go. We know that the dark matter in general is not just made up of point sources, so to say black holes or brown dwarfs, which are like these very faint, basically failed stars, almost like just giant planets that aren't very bright. Because we can go look for lensing events, micro lensing, which is where you would have, if you have a point source going behind something, it's going, the light coming from behind that. Sorry, getting all my hands mixed up. The light coming from behind that would get lensed around it. It would get space get bent by that object, the black holes or brown dwarfs gravitational field, and you can detect those events. And we do, but not enough to make up for all of the dark matter. So some of it is definitely some black holes, but it's a small fraction of the total amount in the dark matter. And you asked some good questions about white holes and the birth of dark matter, and I don't know enough to answer that very intelligently.
Oh, thank you, Deborah. I appreciate that.
Go ahead.
Yeah, hi. Yeah, more of a follow-up to Laurie's question than the dark matter questions. How are you measuring the distance to these diffuse galaxies and the globular clusters? So you can associate these clusters that we see numbered here with the diffuse galaxy itself. If you're just using basically photography, are you using, what methods are you using for distance?
Yeah, there's 2 main ones we're using. The first of which is just the radial velocities. So I don't know how familiar you all are with the idea of cosmic expansion, or that the universe is currently expanding, which it is. And so every point is expanding away from every other single point in the universe. And what that does is it actually stretches out light. So not to get too much into this, because I'm aware it's already 9:30, but the farther you look away from us, the light coming from that is going to be stretched out more and more.
Okay, so you're using spectrometry.
And redder.
Yeah, you're getting redshift,
so we
blue shift.
look
So you're capturing that.
Perfect.
Okay.
Yeah. We look at the redshift, and so we get like its Hubble velocity, and then we can get a distance, approximate distance to where it is. For some of these, it's more complicated, and we need more accurate distances. And then we look at the stars themselves, and we basically plot them on a color versus magnitude diagram. And then we look, stars follow a very well-defined relationship line path inside a color magnitude diagram. So you can look for how old that whole group of stars is based on where they fall, called the tip of the red giant branch method. So that's the other way we do it.
Okay, thank you. I was wondering if the fact that these things were very hard to detect made that more challenging.
Yes, it is challenging. These methods are a little bit, especially the tip of the red giant branch is a little bit debated, but we have, this result on the left is controversial. But we did, as part of the team, of course, I'm biased, but we did do a pretty rigorous job determining its distance. But I won't talk about the controversy right now. I should probably move on if I still have time, Margie.
Yes, you do.
Okay. Okay, I'm going to move on to what about outside of galaxies? And this is where I've been focusing my research on for the past few years. And I'm going to try and kind of go a little bit quickly through, but feel free to stop me again if anything isn't clear. So here, the idea is dark matter is really noticeable on large scales because it's a very diffuse thing. But as you build it up over larger and larger scales, it has more and more of effect. And especially on large scales is where gravity dominates. And that's how dark matter interacts. It's through gravitational forces. So what if we look at something even bigger than galaxies themselves? And that is basically the cosmic web. So this is a similar image to the Hubble deep field that I showed at the beginning, but this is a simulation. So this is a simulation of the universe that was run by the Eagle project team. And every bright spot inside of this image is stars and galaxies. But as I mentioned, of course, stars aren't the only thing. There's also dark matter and gas. And if we looked at the same patch, so in the simulation, but looking at just the gas inside and the dark matter inside the simulation, this is what we would see. So there's this huge filamentary structure that basically fills our whole universe, and galaxies and stars form at the nodes of this structure, and the structure is called the cosmic web. And this is theoretical because this image has never been taken in real life because the gas itself is emitting so faintly that it's very, very hard to detect. It's practically impossible to do it with current facilities. The question is that I am working on addressing is whether we can do that with the Dragonfly telephoto array. So I just wanted to provide a little bit of background for those of you who might not be familiar with gas emission. So the idea is that stars emit over the whole visible spectrum and on either side of it as well, whereas gas itself only emits a very discrete wavelengths of light as the electrons inside the atoms of that gas cool. So the electrons hop down in energy level and they emit a photon at the exact energy of that energy level transmission. So it's just one wavelength basically for that energy transition. So you end up getting basically a fingerprint of these wavelengths. So fingerprint of these lines for each element because they have different energy levels. Okay, I'm going to stop going into that. So the idea is that in order to actually image just the gas, what we need to do is to filter out all the other wavelengths of light and to just pick out that one wavelength emitted by the gas that we're interested in. And the narrower we make that bandpass, the easier it's going to be to detect this gas emission that you can see an example here of a nebula, I think. And so the narrower filter, the better detection we have. So what I worked on initially, I actually used the Eagle simulation to simulate the H alpha, so the hydrogen emission from a specific energy transition called this emits in the line called the H alpha line. So hydrogen emits in many, and we're specifically looking at H alpha. And it was able to simulate what that would look like with the Eagle project simulation and make a mock observation of what Dragonfly would observe if it looked at the simulation. And what basically we found from that is that Dragonfly would be able to see this huge cloud of gas emitting H alpha of surrounding a galaxy. But in order to do that, we would need ultra narrow bandpass filters. So filters that are narrower in wavelength than what you can use with conventional telescopes. And I'll just go into that quickly. The idea is that in conventional telescopes, this is just a picture of one of the units of the Dragonfly telephoto array. We put our filters behind all the optics. So there's a handy filter slot, and that's where the light gets filtered in wavelength space. But at that point, what's happening is that all the light is converging, it's focusing onto your detector. And these filter transmission profiles are designed to be used in collimated light, so where all the light is coming in parallel. So what ends up happening is as you make that filter narrower and narrower, what you actually get from the light coming in at converging angles, so light's coming in at different angles of incidence, is you get a different response for each of these lights, for each angle of incidence the light is coming in at. The reason why this is happening is because typical narrowband filters are interference filters. And as you make that filter transmission profile narrower and narrower, what you actually get out of it, the effective transmittance of that filter when you put it behind all your optics, is this blue dashed line. So it basically becomes even more and more degraded as you narrow your filter. So people generally stop at 3 nanometers and don't go any narrower, because there's really no point, because if you go narrower, you just end up losing all your transmission and you've spread out your band pass again because of all the light coming in at different angles. But the idea with the Dragonfly telescope is that we could put the filters in front of each of these lenses, and at that spot, all the light is coming in from infinity-ish, and so all the light is collimated. And then we would recover these original design transmission profiles. So this is not something you can do with a typical telescope, because you'd have to make a filter that's 1 meter to 10 meters in size, which is not practically doable. But with the Dragonfly,
Deborah, that would be extremely expensive.
I believe that. I don't know if you could do it. Like, you can't make a lens larger than 1 meter. Like, could you make a filter that's larger than 1 meter?
I don't know. I'm not sure.
know.
It'd have to be parallel as well, though.
Yeah.
Optically flat. So
Yeah.
We need a
That'd be
lot of
difficult.
engineering.
yeah, for sure.
It may not be possible. You're right, I would say.
Yeah.
You can float glass on mercury to make it, because it doesn't need to be curved, right? So it would be flat, and that's the way float glass is made, is on baths of mercury. So
Right.
So you could probably make a very large piece of flat glass. I wouldn't want to carry it.
No, and you wouldn't want to slide it in and then slide it out of place again.
So Deborah,
or screw it in.
Deborah, on your Gen 2, are you putting filters on the front of these lenses?
We are, just like
okay.
in this right-hand picture. So the idea is, because we split up the aperture of our telescope, it's easy enough to make 6-inch diameter filters, and we just put them in front of each lens itself.
So those must be custom. Those are custom filters? Yeah.
Yes,
Even
they are.
those would be expensive, I imagine.
They are. They're about $15,000 each.
Yes.
So comparable to the lens itself, actually.
Yeah. Dave, we get off easy paying for the 2-inch filters that we use.
Yeah, I wish we could use 2-inch filters. Right. So what we're doing is we're mounting on the filters, you guessed, in front of all the lenses. So I designed this hardware which holds the filter at the front, and it also tilts the filter because what we can do is we can turn that dependence on the angle of incidence of the light into a feature instead of a bug. So by tilting the filter from 0 to 10 degrees, we smoothly shift that filter transition profile, and it remains undegraded, perfectly normal at a tilted angle. So the idea is we can scan through different wavelengths with the same filter by tilting it. So we put together a Pathfinder version of this 3 years ago now, and it just had 3 lenses with 3 filters on it, and took a bunch of data. So I wanted to just show that, because we actually just published a couple papers using this Pathfinder instrument, and we focused on the M81 group of galaxies. So we put M81 and M82 right in the center of our field of view, and then we observed it with our ultra narrow bandpass filter. And to target the H alpha line, we tilted it to 12.5 degrees, and we got a nice picture of all this H alpha emission from M82 and M81. You can see these nice outflows from the starburst and these caps. This one in particular had been discovered before. And then if I just smooth that and actually mask all the point sources, what we can also see is this huge cloud of gas. So this is a new discovery for us. We didn't just see the stuff around the galaxy, but also something way farther out. We can also, I want to point out, with the same filter, look at N2 emission, and we just use a different tilt. So with a 7.5 degree tilt, we can get N2 by itself.
So Deborah, does every tilt orientation give you a different frequency?
Yes.
Okay.
Yeah, exactly. So we can scan through, it's not a large range. We can scan through about 10 nanometers, which isn't huge, but it's respectable for sure in the local universe. We can basically target about 50 megaparsecs from us. So we go from local, like 0 velocity with respect to us, all the way out to galaxies that are 50 megaparsecs from us. So this is the image together of the continuum with this H alpha shell over it. And that's was just written up and published like 2 weeks ago, actually. Yeah, it's very exciting because this had not been seen before, and especially not gas on this scale. So we currently have a full version, which is under construction. So these 2 on the right are the original Dragonfly, and then these 4 mounts are the upcoming Dragonfly spectral line mapper, that's what we're calling it, and we'll have 120 lenses, so 30 times 4 mounts, all equipped with these ultra narrow bandpass filters. And the filters we're going to use are 0.8 nanometer filter width filters, and we're going to have both filters targeting the H alpha line, which also gets N2, and we'll have ones at about 5,000 angstroms to target O3. So we'll use both on Sky. And tomorrow I'm flying down there with three students, and we're going to set up the first 10 lens of this upgrade. And that's going to have all of basically be a big testing and commissioning run, because in addition to all these ultra narrowband filters, we have a lot of calibration filters, because we really want to get down to those low surface brightness limits. And that means removing all sources of continuum, all the sky, all those background galaxies, all the foreground galaxies.
So Deborah, do you have all your lenses now, or do you still have to order some?
We have them all, but they are arriving in batches. So we have 30 right now in New Mexico, and we have 30 filters. And what we're waiting for actually is the machining. So, and the mount. Right, so we're going down and we're putting it on that the mount that I showed earlier with the 3 lens. We're just going to use that again for 10. That's about the max you can do with that little mount. And then once we have our bigger fork mount, like you can see here, we'll put all 30 together, and that'll be about in the end of April or early May. Is when
Will
we'll be
you
going
will
back
you
to them.
document the construction so that we could see it?
Yeah, I'll
Ah,
take
perfect.
pictures, and we'll take lots of pictures, and lots of reporting. Yeah, I'd be happy to share it with you guys as it's happening, or later on, whenever.
Well, we'll have you back for another talk.
Yes, sounds good. And that was my last slide. So thank you very much. I really appreciate your attention and all the questions. It was really great.
Thank you.
Thank you very much.
Okay.
Thank you, Deborah. Are there any other questions that participants would like to ask Deborah? Great. So thanks a lot. That was really informative.
Yeah.
We will continue with our meeting, and you are an hour later than we are, so you're welcome to stay, but you're also welcome to depart if you would like to.
I better go. I have an 8 a.m. flight, so
Yeah.
I should probably try and get to sleep.
Have a good
before
trip.
that.
Yeah, have a great
But
trip.
thanks so
And thanks so much. Nice to meet you
Yeah.
online.
Great to meet
Thank
you all
you.
too. I'll touch base later. Have a good one.
Well, thank you for setting that up, Margie. That was very informative, because I'd heard about Dragonfly, but never seen sort of that level of detail. So thank you again. That was very good.
Yes, and I can thank Randy, because Randy was the person who suggested Deborah to me.
Ah, very good. Okay, I just have a couple of things to share. So we'll start with the Edmonton photos for this week. And we'll see if, which isn't that one, it's this one. And what am I doing here?
Yeah, this is from Denny Boucher in Edmonton on March 14th. So he has a 4-inch refractor that he took this picture with. And I think you can see from the stuff beside it that 20 exposures at 150 seconds, and then he pre-processed. I guess he took this a little earlier. What I find interesting is this is NGC 4565, which is that needle galaxy in the Coma cluster. If you look through the image, you'll see all these little arrows that he's drawn on the image. Those are all galaxies. Many of them are in the 17 to 18th magnitude range. So it's amazing what you can do with a 4-inch scope. And this one is from Alistair. He was out after they had their Astro Imaging Cafe. If you look in the upper right corner, there's a real faint fuzzy spot there. And that's Comet 2020 L3 Atlas from his backyard in Edmonton, which is surprising. The last one is from Tom Owen on March the 18th. This is NGC 281. He took that under a full moon sky, if you can believe that. 115 millimeter triplet at f7 using a field flattener and a QSI camera. 46-minute subs, H alpha, sulfur, and oxygen for a total exposure of 4 hours. Pretty impressive.
Okay, thank you for those. I will get rid of that. I just wanted to, and I'll put the this web address in the chat, but Jim Hesser brought this to our attention, and Megan Donahue gave a talk at UVic. I guess was that last Wednesday, and pointed out that there's this Galactic Atmospheres gallery. And Jim thought it would be interested for those of us who like photography and various things to have a look at some of the things they've got in there, because they've come up with some great images and simulations and exhibits. So I will put this into the chat, this web address there. There's also a forum for the research community. So it was very interesting to see. I don't know if Jim wanted to say any more about it, but I'll just grab this right now anyways and stop the share. And I think David Lee, you are next.
Great, thank you, Chris. I'm just going to show you a couple of things. Also, there are 2 SIGs this week. Dave Payne's chairing the astrophotography SIG on Wednesday, I believe, and then there's the Makers SIG on Thursday. Okay, so, oh, you're not seeing the thing that I want you to see. Oops. Let's try that again. Okay, that's better. So I just wanted to let you know what we're going to talk about on the Thursday night Makers SIG. I got this suggestion from Gary Sedun. He was asking me about microprocessors and sensors. So I thought it'd be a good time to maybe talk a little bit about the use of some of these microprocessors, especially this particular set of Arduinos. I don't know if people have heard of these microprocessors, but they're used commonly for Internet of Things type development, and it has lots of applications in both citizen science and also in just general telescope making gadgets and stuff. So I'll probably give some information on that. Now, if you don't belong to the Makers group, just let us know and we'll send you the link to that. So that's Thursday at 7:30. And the other thing I wanted to tell you about was I'm sort of very quickly exploring citizen science here in Canada. So that's actually, you'll see on the screen, the Government of Canada Citizen Science portal. There's also a portal in the States called SciStarter. But I think I probably will maybe call a special Zoom session just for anybody who's interested in participating or creating some kind of project that involves citizen science. So those are the 2 things I wanted to tell you about. Dave, do you have anything to say about the Astrophoto SIG?
Yeah, it's good. There's a lot to talk about this Wednesday. One of the things I believe Barton's going to give a little talk on how deconvolution works. We've got a lot of photographs that have been a lot of images been recently taken. We're sharing them, and if you've got any questions, you're interested in astrophotography, maybe not to the scale of the presentation we just saw, but please join us on Wednesday.
Okay, thanks, Dave.
And thank you, David. Anything further there? Because if not, we'll move over to Chris Gainor, who has some updates from the wild world of James Webb.
Hello there. So yes, I've said this before, but I remember when they finished kind of getting it into the right position, that, oh, we're not going to see anything until June, and they've been that has not been the case. So anyway, on this slide, I just draw your attention to the image at the right, which shows the star, I think in our Ursa Major, that that JWST has been focused on while it's been going through its commissioning process. And just to refresh yourselves, in February, we started to see the process of the mirrors getting lined up. They were pointing in all sorts of different directions, as you see at the right there, and then the images at the left, and the one at the bottom center there kind of shows the mirrors pointing in slightly different directions, but you can see that one is very bright and it's looking at that star in the map we just saw. So and then I've shown you these slides as they've gotten more aimed better and better focused. And then last week they issued these two images, which are just gobsmacking. So the one at the left is similar to the one I just showed you in the previous slide. Now everything is aimed at that star. So that reflection is of that star, which you see in the center of the image at the right. And usually JWST will not be looking at anything that particularly bright, but of course the real fascinating thing about this is not that star, but the background. Take a look at all those galaxies. And somebody said, you know, it's going to be, you know, practically every image from JWST is going to be like the Hubble Deep Field. It's just amazing. So anyway, the telescope has kind of cooled off. Still a little ways to go, but now they're setting up the alignment for each individual instrument. There's the 4 different instruments on it, not to mention the guidance sensors. So now they have done the alignment for NIRCam, and this is what you see in this incredible photo at the right. Now they're moving on to lining up the guidance sensors, which of course come from Canada, and the other 3 instruments. And this is going to take a while, because they're saying still no science until June, but we've already got this amazing photo, and they've been doing various checks on things, and everything is nominal. You know, it's as good as they hope for, and where it isn't, it's because it's better. So so far it's just going great. This is the field of view of James Webb, and the instruments all look at different spots in this field of view, and this is also something we have in common with Hubble. There's a similar map for the instruments, and so you can see. Let's see, NIRCam. You can see the field of view here. This is just what we were looking at, and the fine guidance sensors I mentioned, and the other instruments are here. So those are the alignment and focusing for those instruments is getting underway now. And just this is kind of where we're along in the commissioning process. Just the number 6 here is basically today, and you can see how far along things have come, but we still have a ways to go until we get to June. And then this slide here just highlights the other Canadian contribution, which is NIRIS, which is down here. That's one of the instruments that will be aligned in the next little while. So that's basically my my update for now. I wouldn't be surprised if we as they line up the individual instruments, we might be seeing some test images from them. No promises, but that seems to be the way they're working. So anyway, I'll probably be back. I'm going to be out of town next week, but I may be back in a couple of weeks with more images. So that's what I have to say for today.
Chris, Gary, sit down here. I have a question for you. Could you please put the second slide up again?
Okay.
That
This
one
one?
there. No, the next one, the next one. Go, no, sorry, yeah, they're right there. You said the middle thing there, that's the completed segment alignment. So are you saying that each mirror is not focused at the same place on the secondary, but a different place, and then they simply stack them?
Okay, these are what they did is that, you know, when they started out, you have these 18 segments and they were pointing all over the place.
Yeah, right.
So then they set it up here so that they would get a look at each of the individual mirror segments, and then at the right they lined them all up. But that's only part of the process. There has to be some finer work done, and that's what they're doing now, and they're well into that part now.
Okay, so it does form one continuous curved mirror looking at the very same spot on the secondary, just like
That's right.
does. Okay, good.
That's right. And I think, you know, I mean, I was, you know, really impressed with Deborah's presentation. You know, I mean, so much of the stuff that's going on now is because we have this amazing computer power available to us that makes stuff like this possible, and stuff like Dragonfly possible. You know, not to mention even Hubble, you know, which is kind of an old fossil now. It has a lot more power on computing power than it did when it was launched. So anyway.
Yeah, thanks.
Great, thanks, Chris. Dave Payne, did you want to wait till next week?
Yeah.
Okay. So maybe I'll ask for the concluding comments tonight then from Jeff to tell us a little bit about next week, because we have another speaker 2 weeks in a row.
Super. Thanks, Chris. So the speaker next week, I didn't realize at the time when I was setting it up, but it really can be seen as a spin-off from Randy's presentation last week. As you recall, with Randy talked about an autonomous underwater vehicle, an AUV, finding Shackleton's boat, the Endeavour, and then went on to talk about the navigation. I was at a presentation at UVic in the fall. It was a Canadian cave diver who's been doing a lot of work around the world. One of the dives she did was a test of concept of an AUV. And the interesting thing was to do mapping in the cave, in a cave that really divers couldn't penetrate. It was just too dangerous. The interesting thing about the AUV, though, was it was created by a group called Stone Aerospace. There's a few manufacturers of AUVs in the world, and this was the first one I'd seen with an astronomical connection. So I looked into it a little bit, and Stone Aerospace is developing both what they call cryobots, that is ground penetrating or ice penetrating robots, and AUVs intended to explore ocean worlds in the solar system. And their target is really Europa. So looking into it further, they've done a series of projects with NASA, each one simulating different parts of this in what they call Earth analog environments. I wrote Stone Aerospace and just to see if they would be interested in that or able to talk with us about the kind of technology, the problems they've overcome, and the problems that they anticipate as they move forward. And I got an incredibly gracious reply from a gal by the name of Vicky Siegel. Vicky is actually the director of the robotic field experiments. So she's the one who has agreed to speak with us next week.
Great, thank you very much. So I don't know if anybody else has any final comments tonight, but thanks again to Margie for arranging a wonderful speaker. Oh, from Lori. What did we say here? Sorry. Yeah, unfortunately, Randy's not here tonight, as you noticed. It's a so we'll have to. But we, yeah, I guess we need to talk about getting ready for our astronomy day. And for those on council, there is a meeting next Tuesday, so it's. Don't know if there's going to be one before then.
It's getting a little
Yeah,
late.
it is getting closer.
We don't even start to think about it until after that meeting. We've only got about 4 weeks to go after that, so it's pretty.
Yeah.
Anyway.
Not sure. I hadn't heard anything more about that, but yeah. So I suppose you could reach out to. Do you want to reach out to Randy and?
I could. There's lots of different moving parts. If we want to do anything, then there's lots of moving parts that need to be done. Okay.
True enough.
Thanks.
Yeah. No, thanks for bringing that up. Yeah.
Just closing comment and a thanks to Chris, because Chris sent me a link to the website where one could report light pollution from nearby streetlights. And I passed along to a friend who's up on a hill, and the streetlight across the street was beaming right into their living room, obscuring their fantastic view they have over Victoria and of course the sky above. So he sent a request in to have a shield installed, and Sanex was there within 3 or 4 days, and he is so happy. So thank you, Chris.
Oh, you're welcome. Yeah, if those of you who live in Saanich, yeah, get in touch if you have any issues, because they have been very responsive to that. I'm sorry to hear that. I think in Sydney it has not been so responsive, but
Victoria City is also quite responsive.
Yeah, Sydney doesn't because their contract is with BC Hydro, and BC Hydro, the fixtures they put in, they don't have shields for them.
Right. So they'd have to try and make something, I guess, and attach it, which they're probably not willing to do.
No, they'd have to be CSA approved and get wind tested.
Yes, an issue. Okay, well, thank you all for attending this evening, and thank you for people who asked great questions there, because that, again, I thought that was really informative and an interesting approach to solving a problem. And I'm glad to see that they're having success. So, so we'll see you next week. Another speaker, and Dave's topic next week too.
Hey, everybody.
Thanks, everyone. Take care.